And then after the visible wavelengths of light, which are the ones that our eyes are able to see, then you have the infrared, which are higher energy wavelengths, and that's why they can burn our skin. And then you have X-rays, which allow you to even look at the bones inside of our body. And then finally gamma rays, which are very, very high energy. And luckily they're blocked by our atmosphere and never get to the Earth, because otherwise they would kill us. Same with the X-rays, those are blocked out. Most of the infrared is also blocked out, except for a very little bit right here, and that's the part that gives you sunburns, because it's high enough energy to damage your skin. So those are all the different types of light. They all have different energies, they all have different wavelengths, and they all have different frequencies. If you are high energy, then you are high frequency and low wavelength. And if you are low energy, then you are low frequency and high wavelength. So high wavelength is low energy. Those are the ones that don't hurt our eyes at all. Alright, so now that we have a good feeling for what light is with respect to being a particle as well as being a wave, we have to talk a bit more about light so that we understand it, because light is very exciting. To understand this, what we first want to realize is that let's talk about visual wavelengths of light, since these are the ones that are most important to human beings. When light is coming down from a man-made light like the ones in my house here, that is what I would usually refer to as Roy-Jabiv. Roy-Jabiv say Roy-Jabiv is red, orange, yellow, green, blue, indigo, and violet. And you should know those in order forever. Roy-Jabiv is that big of a deal. So Roy-Jabiv is coming from the sun. If you have the sun up in the sky, you've got entire Roy-Jabiv. Every single color there is, every visible wavelength of light is there. Every pink, every green, every blue, every yellow, all of the different wavelengths of light are there. That's called a continuous spectrum. And the only true continuous spectrum of light is the sun or another star, because they contain all of the different wavelengths. So if you looked at them through a prism, they would be continuous. There would be colors at every different spot, and this would be like a rainbow, where there's no breaks in the colors. All the reds are there, all the yellows, all the greens, all the blues, everything's there. The light that's man-made, like the light on your phone or this light coming off of my house, is very different. It's going to have subsets of light. So it might have some red and some orange and some blue and a little bit of indigo and maybe some green. In other words, we'll have a bunch of different colors mixed together. When you mix a whole bunch of colors together, our eye interprets that as the color white. There really is no color white. White is the presence of a whole bunch of different colors all at the same time. And when that enters our eye through the hole in our iris, our brain interprets that as the color white. It is all, however, not continuous. This is a non-continuous spectrum of light. And it just has subsets of light that when mixed together, our eye interprets it as white. And that's why it looks like it's nice and white all over my room in here. So that's pretty cool, because that means that when you have a light on, all these different lights are coming down. So here you can see my little puppy dog. Notice he's sort of pinkish red. My son made this. Okay, so here's the puppy dog, and Roy-Jabiv is coming down from the light, and it's hitting the puppy dog. And the only wavelengths of light that are reflecting off the puppy dog into my eyes are sort of a pinkish red. And so my brain says, oh, that's a pinkish red dog. And then you would ask, well, what happened to all the other wavelengths of light? They were all absorbed by the puppy dog. So the chemicals and the things that are in this, the dyes that are in this color, absorbed all the other colors, and the only one that was left over was this one over here that gave you the pink color. And that's why this came off as being pinkish red. Here is another little cute little doggy. He's black and white. So let's look at the white part first. That means Roy Jabib is coming down and hitting the white parts of this doggy, and everything is reflecting. All of the wavelengths are bouncing off the white doggy into my eyes, and so I interpret that as white because all the wavelengths are mixed together. In addition, nothing is absorbed by the doggy. None of the energy from the light was absorbed if it's white. However, here's some little black ears right here. So that means Roy Jabib's coming down, it's hitting the black on the little doggy, and that means now that nothing is coming into my eyes because the absence of all wavelengths of visible light, my brain interprets as the color black. There is no color black, it's just lack of all the other colors being there. So if you have an area where there's no wavelengths of light bouncing into your eyes, then your brain interprets that as black. And it means all of the energy was absorbed by the doggy's ears. This is exactly why I like white t-shirts so much. Because when you wear a white t-shirt, all of the light is reflected off and none of it is absorbed, and so the shirt stays nice and cool. If you have a black t-shirt on, it absorbs all the energy, and a black t-shirt is much more hot than a white t-shirt is. Alright, so we now know about Roy Jabib, we know about continuous spectrum, we know about non-continuous spectrum, and we know about how things create the colors that they have, because certain chemicals in the paint will absorb certain wavelengths of light and remove them, and then that leaves some wavelength of light that goes into our eyes, and we interpret that as the color of the light. This is really interesting because the brain can get different. For example, if you're colorblind, it means that you don't see a whole spectrum of wavelengths of light at all. And so some colors you literally don't interpret there as all, and they usually have some shade of gray that your brain interprets it in. In very, very, very rare cases, there are human beings where the spectrum is inverted. And so if you show them something red, it actually looks purple to them because this whole way of interpreting the light has been inverted. And there are a number of other very strange genetic changes that can change your interpretation of light. Now, the visible wavelengths of light range from about 400 to 700 nanometers. Nanometers. So this is a very, very short wavelength, which means it's very low energy, and that's good. That way it doesn't hurt our eyes when it enters. Remember, these would be the wavelength.